have a look at this concept of gravitational fields and how we might represent those fields diagrammatically. So we define a field as a region that experiences a force. So we can have an electrostatic force and we can represent an electrostatic field. We can have a magnetic force, we can represent that as a magnetic field. We can also do the same with gravity. So we can say that if an object sits inside and is experiencing a gravitational attraction to another object or another mass, then there will be a gravitational field as well. And the closer those two objects are, the stronger that field will be. The further the objects are apart, the weaker that field will be as well. So to represent this diagrammatically, we first of all have what we call a test mass, and we call that M, and we make that a very, very small mass. And that ensures that our other mass that we're representing here is much larger, and therefore the acceleration will be from the small object to the large object. So in this simple diagram here, this could be a representation on the surface of the planet Earth. So essentially we've got a flat line. If we made it much larger, obviously that line would be curved, but we're only taking a small section. So our small test mass will obviously fall to the larger mass Earth, and it will accelerate through that process as well. Now there are a few things that we also represent in this. First of all, if we're on the surface of the planet Earth and we haven't moved a great distance, then we should have equidistant field lines. And that equidistant field lines means that our field strength is the same or is uniform through that cross-section that we've just shown. The second thing that we also show with these field lines is direction. And in this case, if we put our test mass M here, it's going to accelerate toward our larger mass at the bottom. So the field lines will show us that direction. So what about we represent this in a slightly different way, and this time we're going to have a sphere. Now, if this is a uniform sphere, our centre of gravity will be at the centre of that sphere. But obviously, if we have an irregular object, our centre of gravity will lie somewhere else. Now, in representing field lines in a sphere, we would once again represent them with a test mass M up here. We could have it over here. And that test mass, because it's smaller than our larger mass, will obviously travel from that point, accelerate through to our larger mass. So we've shown direction, and you'll notice with two test masses here, they have different directions. So the direction that they travel is through to the centre of gravity of our object. Because it's a uniform sphere, that just happens to be at the centre of our sphere. However, if our centre of gravity is not at the centre, and let's say it was here, then our field lines would be pointed toward that centre of gravity. Now once again, we have multiple field lines, but we have a slightly different picture to what we got on the left-hand side. Here, our field lines represent direction, but they also represent density, which equates to strength of field. So we'll notice at the surface here, the distance between these lines is less than if we move out to these points here. So what we can say is the field strength at the surface is much greater than if we move out. And if we think about that, as we get further and further away from the Earth, the acceleration due to gravity is less. In other words, the field strength is less. So this diagram shows an accurate portrayal of what's actually happening with the gravitational force between two objects. Now, we can also say something else from this. We can say that the gravitational field strength is defined as force per unit mass. In other words, we rearrange our equation of F equals ma, where we substitute a in for our acceleration due to gravity, and we call this g now, even though we know it as acceleration due to gravity, we can also refer to it as gravitational field strength. So we know that at the surface we have the highest gravitational field strength on Earth. If we move out 1 kilometre, 2 kilometre, 3 kilometre, 20, 30, 50 kilometres, that field strength gradually decreases. And what we see is a decrease in this acceleration due to gravity number.